And the rule depends. Oh yeah, start the recording. So select applies the index unary op. The rule can
You're a
depend
little
on
out of focus,
I.
unfortunately.
Oh
All I
yeah,
see is
I need to,
there we go. There we go.
when I remove my hand, I need to change the focus somehow. I don't know. Yeah, I forget to do this before. And if I do it now, it'll take me 10 minutes to get the focusing correct.
Right.
So
I see it now.
it
Yeah.
and it depends on, the thunk, or let's call it theta, because that's a better, thunk is weird. People don't like thunk. And so theta, some scalar, right? Well, the problem with that is what if I want to pick an edge? I've got an edge from I to J. There's methods in GraphBLAS or LA Graph that already do this. I want to keep that edge if some vector P of I is not equal to P of J. Like I want to keep all the edges that cross components to go from component 3, like you're in component 3, you're in component 4. Okay, keep it. We can't do that yet. We need a select that you can have, or a Cartesian mask. You have a matrix, and I want to put a vector, say W, and a vector V here or something, and I want to have a rule that says pick that if those vectors, pick Aij if V sub I and Wj say you can.
I see.
Something like a Cartesian mask. Imagine
Yeah.
imagine a mask being formed by V W transpose. It's a matrix, but it's a rank 1 matrix formed by some implicit product. That's another way to think of it as a
Is this
Cartesian
what
mask.
Scott referred to as like input masks, potentially?
Uh, so I think it's related. We don't have an input mask either. I think there's some connections to this with input masks. Input masks, I mean, if you fuse, yes. But then if you fuse, you can do anything, right? You can output mask be the input mask of the next method. So yes.
Right.
But this it's just a simple built-in method, an extract that's more extended like this. And so anyway, my point is once you have a little bit more, I think a little bit more control in GraphBLAS for this kinds of operations and maybe others, I think you get to a point where dynamic graphs, truly dynamic graphs that are just delete the edge, keep the edge, delete the edge, become less critical because you can always flag the edge as saying, I don't want that edge. How do you flag the edge? Well, like you said, an input mask or a Cartesian mask like this. Like I want to work with these edges that have some property based upon some selection of nodes and columns or some rule that depends not just on the value and the position of the entry, but on some other pair of vectors. You can think of GRB extract as working this way too. Like extract, you sort of tag the matrix and you say, give me these rows, give me these columns. How do you specify the rows and columns? Right now, it's the silliest way you can imagine. It's a pointer
It's
to a
awful.
C. It's
Yeah.
awful.
It's awful. Yeah. It's
The
basically
same
not
thing with a
useful.
sign. Those row indices, those pointers to a raw C array is a bad decision because it's a non-opaque data structure. I can't
Yeah, that's bugged
optimize
me
it.
for years.
I can't keep track of it. I can't know what's in it. I can't know about properties. Every time you give me a list, I have to evaluate the properties of this thing to use the right algorithm for it. I mean, it is just ridiculous.
The other thing I hate about extract is that it reshapes the output.
Yeah, exactly.
Yeah,
Exactly. Well,
it's
select
broken. It's
does it.
broken. Yeah.
Yeah, select. Yeah, it's yeah. So you want to select, you want to extract, but you want to keep the same dimensions. Right. It's kind of like it's like this is kind of what extract should have been.
Yeah, I agree.
Now, having said that, the way extract is written right now actually does make sense in other contexts. I mean, if you look at the MATLAB definition of C equals AI comma J, it is GRB extract or GRB assign. It's the simplest thing out there, and people use it, but not as much as I thought at the beginning. And so it was really crazy. I spent all this effort into GRB extract is not so hard to write. It it took me some amount of code to write GRB extract. If I look at the source,
Yeah, but extract also, it's not useful for hypersparse because you can't have these 2 to the 60 C arrays, right? You gotta,
no, you
yeah,
can't.
the only way around it I found was to do a GRB all and with a mask.
Hmm.
And
Yeah,
that, but that's not
yeah.
nearly as useful, yeah.
Extract is pretty simple. It's 2K lines of code, and that's a lot already, but it's reasonable. Assign is a beast.
Yeah. Oh yeah, I believe it. Yeah.
Assign
Uh,
is this is it. This is ridiculous. I got 44 at least different methods for assigns. It's crazy. We're not going to talk about assign today. Anyway, I think these kinds of features would make dynamic graphs less critical to algorithms. Um, so having said that, then when I came to GraphBLAS and saw this is what they want me to write, my thinking was, okay, I see, like set element, extract element as scalar operations. Okay, that tells me you want a dynamic graph, right? Well, that's going to be dicey. So let me put in a data structure that's mostly static with a little bit of dynamic features to it. And that's my pending tuples, my zombies, and so forth. I put that in the very beginning, actually, because GRB set element was a method. You just want to go boink, stick it in. Well, there's no way that's going to be fast if it's totally static CSR. And so I thought, well, it's not really very hard. It's opaque. Hey, it's blocking mode. Hey, perfect. I thought you stick an entry in, I'll say, thank you very much. I'll do it later. I'll just pocket it in the list, and it's super simple to implement. I implemented that right away at the very beginning of GraphBLAS. And it's been very helpful. And I use it other places than just set element as well. Um, and it's very fast and insert a bunch of entries. And believe me, and I use it here actually in assign. When you do GRB assign, most of these methods don't finish the work. Most of these methods do assign into the entries that exist. They delete things that exist that should no longer exist, and things they want to stick in, they make a set of pending tuples as a group, as a batch. And then I'll finish the work later. Almost all of these methods, except the bitmap ones, they can just right away zap them entries. Almost all of the assign methods use that feature. So it was from the get-go put in there, but that's the most dynamic I got. And okay, so let's dive into the JIT then. That's a
JIT.
dynamic matrix collection. Let's do JIT. We got coffee, we can do JIT.
Yeah, I'm just about to pour a cup here.
Yes. Okay.
And just one further question before you get started. Do you feel like this is a 2-session subject or?
The JIT, yeah, the JIT's going to be big.
Yeah, okay. So if you want to sort of break it up, mentally as you do it
I
with the idea that we'll do another session.
Yeah, I will think about that. It's it's 12, it's 11,000. The JIT itself is 11,000 lines of code, and that does not include yeah, that pretty much includes, and the gateways into the JIT functions. All right, that doesn't include that. It includes most of the JIT is 11K lines of code. So it's a big beast. And So I will try to keep that in mind as we're, the 2-session thing. I'm not sure, just looking ahead, how, how where I can, because we're doing this on the fly. So let me just dive in.
Yeah, and I'll come back with questions for the next session too to see if
Yeah,
that helps out.
yeah. Now, so the way to start with the JIT is to start with the simplest, interesting GraphBLAS function, which is GRB matrix reduced to scalar. Right? That's square one reduce. And also, because I know that that's an interesting way of diving into the JIT, I actually have some comments in the code along those lines that say, look, this is how the JIT works. And I have, like I have these comments that look like code. They're not code. So you can kind of see what's going on. Self-documenting code that includes comments that is code in reduce. Okay, so reduce is really important. Let me go to first, before I go any further, let me go to my JIT cache and clear it. So this is my home directory hidden away from the user, is the JIT cache, I call it. It defaults to .SuiteSparse. If you're on Windows, it's local app data or something like that, environment variable I get it from, and it works. The JIT works on Windows for that, using that. So I have no JIT kernels, right? And we're talking version 3 now, 9.3, which is, it's not yet released. 9.3 is not released, but that's the version I'm using right now. So it's still under construction. It's getting close to being released. And this 9.3 has all this code reconstruction, code reorganization. All right, so let's go to reduce. Where does the JIT come into play? Well, I think you already saw, matrix reduce. I think it calls then this one. Yes. So GRB matrix reduce is this is a macro that generates all those silly C types with scalars. But here's say a better method, that ought to have reduced to a monoid. Here we go. This is the primary method right here. Reduce a matrix to a scalar, a GRB scalar, using a monoid. Okay. So we're going to call, to do that, we're going to call scalar, where is scalar reduce? Let's see. So that calls this method. We're not close to the JIT yet, but I just wanted to go from all the way outside how we're going in. So the very first thing I do, reducing to a opaque GRB scalar, super simple. If there's no entries in the matrix, the output is empty. So I make sure the scalar is either bitmap or full. So I have a place to put my answer in a simple way. The scalars can have different formats, which sounds kind of silly, but there it is. You need to have an empty scalar. Interesting thing about reduce, by the way, there's no place in the spec that actually needs the value of the identity of the monoid, ever, but in one place. Actually, mathematically speaking, numerically, computationally, I use it a lot, but I don't actually need it but for one place, which is reduce a scalar to a matrix when it's a non-opaque C scalar and there's no entries in the matrix. Then I have to, the spec says, write the value of the identity of the monoid into the user's output. That's it. So here we don't have that complexity. If the answer is empty, then the scalar is empty. Okay, so then I get to reduce to scalar. And reduce to scalar, yeah. So there's the scalar. I know the type of the scalar, and there's an accum operator. We'll do that. This is the main thing, the monoid and the matrix. That's the thing that's going to reduce the matrix to the scalar. So we get now, we're not yet the JIT, but you just got to kind of see all from start to bottom where this has to be fast when there is a JIT that's already pre-compiled. I got to get to it quick because I've got it compiled and loaded in memory. I want to find it and run it right away. I don't want to have a long process of figuring out which kernel of the thousands I have. I'll use that one. Right. So this decision has to be made very quickly. So finally, we get the reduce to scalar code, which you've seen before. Do the error checking and so forth. All this has to happen. If I have CUDA, I can call the CUDA kernels. If I don't have CUDA, finally, so I'm not yet at the JIT. Where is the JIT? Okay, finally, I can decide, and there's a couple of reductions that don't need the JIT. In particular, this method, which I just found a bug to. It was kind of crazy. I was demonstrating the code to someone, a student intern, and showed her what the JIT could do or the reduction to scalar could do, and I got the wrong answer because of integer overflow.
Oh man.
And yeah, well, if you have a full matrix that's bigger, has more entries than like 2 to the 64, which I can do, right? An ISO full matrix takes order 1 space to create and represent. I can compute on it. I can reduce it to a scalar, and I got the wrong answer. And so I had integer overflow. This is this method. So I have a monoid. It doesn't need the JIT. I just need the function pointer because I have a billion values to reduce, but they're all the same. Like I'm summing them. Well, I can do log n adds, right? Like compute x to the n, where x is then that's converting the times operation into power. Well, I don't do that. I unroll that into repeated applications of the times monoid, log n times, to compute x to the n.
Mm-hmm.
The same thing would be true if the answer should be n times x, like sum up x value x n times. The answer is just n times x. Well, yes, but that just works for the plus. And what about overflow? So I don't do that. I do the summation, log n times. And
Right.
that's what this does. So this does not use the JIT. Then do I have a factor kernel built in, precompiled? That also does not use the JIT. That's my factory kernel. And that's that big switch table that decides which precompiled method I'm going to use. And if the GraphBLAS is compiled in compact mode, you don't get any of these. You just bypass it. And then, info no value means, and this is throughout the code, internally, info equals no value means I haven't done the work yet. So if a method above has decided, hey, I can do it, then it returns the info value, and it won't return no value, it'll return, success or failure of some kind. And so this means no one's got it yet. Okay, the JIT comes in and says, oh, let me do it. And if the JIT refuses to do it, then I use the generic kernel, which is function pointer. So that's super slow. So this now is the access to a JIT method. And it's all the methods that access this are underscored, they're suffixed by underscore JIT in the namespace. So if I go to, and that's important to see as well. If I go to GraphBLAS source, I've got this thing called the JIT wrappers here. These are my 40 some odd JITs wrappers, and EY's, GRB reduced to scalar JIT is in there as well. I could put each of these underscore JIT methods in the respective folders. This is not in the reduce folder. There, I put them all together. And the reason I put them all together, if you look at the source code, they're almost all identical to each other. They're very similar to each other. And so let me show you what that looks like. And basically, I've already potentially, so there's the input problem. It's the monoid, and there's the output scalar. Okay. But I've also already done some analysis. I've decided how many tasks I'm going to create, how many threads, OpenMP threads. This is not the CUDA JIT, that's up above. How many OpenMP threads I'm going to use. I've allocated myself some workspace that the JIT is going to need. Some of that could have been done inside the JIT kernel. I already had it outside, so I left it there and passing it in. So I may have done some symbolic analysis here of the problem outside the JIT. That's true for any JIT or any kernel, factory or generic or otherwise. And now I'm just passing in that information to the JIT. Every JIT method is going to have its own API. I mean, obviously, this is not going to work for matrix multiply. So now, reduce to scalar JIT, this is now in the JIT wrapper. Now we're into the JIT. Okay, so I have the problem. This is basically the problem specification for reduce. The first thing you see is this rather strange macro usage. It's a type def of a function pointer to the function that's actually going to do the computation for me, the JIT kernel itself. Okay. And what does that JIT kernel look like? Well, I've just obliterated my JIT. So let me compile GraphBLAS, make sure it's compiled, and I'll run a JIT example. I'll run my I'll run my Gauss demo. I think I've got CUDA turned on, so it's going to take me a while. It's going to compile a bunch of CUDA JITs. Yeah, it's compiling some CUDA JITs. It's going to take a while. So while that's compiling, so this is going to be slow. But so I have the input specification, and it's a 3-step process, and every function that ends with underscore JIT is going to look just like this, and it's going to start with this type def for the prototype. What does this prototype look like? Well, it's the reason I put the prototype of the function in, and this is the function at the very end, that the function pointer to the kernel itself, and I call it. And the name of the kernel is always gbjit kernel. And when I look it up inside the function in the library, it's always called gbjit kernel. And so I call it. There's my function, and there's the prototype. And this prototype is what's hidden here. And the reason I hide it in this macro is because I use it in several places, and I didn't want to define it in multiple places. And so I just have it once. I need a pointer to it. I need it prototype places, and so I did a macro for every prototype. It's a little ugly. You kind of, I don't know. So it's a 3-step process, and all the JIT wrappers have this 3-step process. The first thing is the encodify, I call it. I have to construct an encoding of this problem based on the kernel it is, and based upon the particular instances of, like, is it a float matrix? Is it a double matrix? Is it a plus reduction? Is it sparse or is it hypersparse? Is it a user-defined thing? Is it? All these things have to be encoded in a bunch of bits that describe it's this reduce you're talking about. This has to be done every time the method's called, whether it's pre-compiled or preloaded at all. And then I have to get a hash function of that kernel, and then have to look it up in this single hash table, or have every kernel, all of them, every JIT kernel or pre-JIT is in this big hash table that I quickly look up and grab and say, there's my function pointer. And so that has to happen super quick. So that's the encodify process. And once I encode it, I have encoding, I have the hash function. Then I need to look it up in my JIT. And the JIT says, well, I may not have it yet. Let me go compile it. Or maybe compiled yesterday. Let me go load it from disk. It's going to take a while, and that'll be slow. I don't care. First time load, first time compile and load, that could be really slow. But the second time it's loaded in memory, I've got to get to it quickly. So this has to do that quick lookup. And then once I have the function, this thing calls it, does the work, returns the result to the caller. So the JIT then breaks into these 3 steps: the encodify, the JIT, which if it needs to create the source code, I call that a macrofy. I have to make the macros that are the header for that instance, that template of that templatization instance of that method. Okay, so what is the JIT encoding? This is a very, very small data structure. It's got to be fast. Now we're inside the JITifier itself, and this is it's 9,000 lines of code, bunches, and every function in the JIT, it has a phi in the name: JITifier, enumify, encodify. I made an adjective. What is it? Phi. It makes a verb out of an adjective or something like that.
You verbified it.
Verbified it. That's it. I verbified all of these, like encodify, even though they were already verbs. I'm encodifying, I'm enumifying, and I'm macrofying, or demacrofying, which is the opposite of macrofy. But I just have to demacrofy the name. I'll explain why I need that in a minute. And so the first thing you see here is an encodify for reduce. Now, other methods in the JIT will have different encodifiers. And so let me look at some of these, but they're going to be the workflow of a JIT is going to be very similar. Like, let's just go to, I don't know, let's just go to a JIT that wraps the one of my dot matrix methods for matrix multiply. This file looks very similar, doesn't it, to what you just saw? This is matrix multiply. It has the same three processes. It's got always got a prototype at the front. It's got a whole different set of parameters. The encodify is a different encodifier, but the jitterfier is a different jitterfier, different load, different kernel number, and everything. But it looks very fun. In fact, if I do a diff, they're totally different methods. The dot three matrix multiply and the reduce to scalar. But it's kind of helpful, I think, to do a diff between these two and realize, well, look, that's the only diff. Just one's for matrix multiply, one's for reduce. Fine, it still has the same core structure. One's encodifying the MXM, one's encodifying a reduce, and has different, kernel ID numbers and enums and so forth and different inputs, but they're otherwise very similar. And the final JIT is called the JIT kernel, the GB JIT kernel. Always, just of course, totally different parameters because the prototypes are different. So we're in the, let's see, where am I? I'm in the reduce to scalar JIT. I have to encodify it. So let's look at GB. The encodifiers are all going to, so it's a two-step process to encodify a, let's see. I think I need to look at what is the encodifying. There's a JIT encoding, and that includes the enumerification and also includes things like the hash. I think it includes the hash function. Let me look at it. Let's look at jittifier, jittifier.h, JIT encoding. Okay. Yes. So it's what 16 bytes of information in the encoding. This is my hash table entry. Oh no, it's not. It's part of it. It's a critical part of my entry. And this is my JIT hash table entry right here. It includes the encoding. But what's the encoding? The encoding is the enumification of this kernel instance. Okay. But it's also got to have, outside of that encoding, there's more bits. There's the kernel code itself. And every kernel has its own K code, kernel code, a GB JIT code, and that's up above. And also the length of the suffix. I keep track of that. And the suffix is a suffix on the name of the method. And I need that if you are use a user-defined operator or data type. And if you use it, the nice thing about GraphBLAS is if you use a user-defined data type, almost pretty much all the time, you're going to have to use a user-defined operator on it. Not always. There are cases in GraphBLAS where you don't have to, where the operator does not depend on the data type of one of its inputs, just its pattern. That happens, and I can use a built-in method on that input matrix, even though it's user-defined data type. But I have to have a suffix with a string to say, well, which are you talking about? I can't just encode it in a bunch of bits because I have to tack on like, oh, this is the add Gauss operator or the molt Gauss operator or whatever, semmering. I have to put the name of that in the name of the method that goes in the lib file. And so I don't try to pack that down to a bunch of bits. I have to keep the name. But so if you're built in, this is 0. You don't need a suffix. So this is the encoding. And then the hash entry has the hash for the whole problem, which includes the whole suffix if I need it. It's got the entire suffix of the method. And then the hash entry then also has two things. It's two other things. It's when you do DL open, you get a pointer back to that library. And you DL close, you need that pointer. So that goes there. And then I want the function, the GB JIT kernel function inside that library. And that goes there as well. So this is my hash table entry, and it's got to be fast lookup. I don't want to do every time I look up a kernel, I don't want to do a DLSIM to find it in the library. That's slow. I want to keep it cached in the hash table entry. So this is pretty small. I don't know. It's 50. It's 56 bytes. I rounded it up a bit. This thing could have been 32 bits, but it'd be a weird number of bytes, not a multiple of 8. I wanted to make a multiple of 8 to make it simpler to do the math. So that's my hash entry. So I have to the very first thing I have to do to know if I have this kernel is encode it. To encode it, I first have to get its enumerification. Encoding is not much more than this enumerification. It's encoding, enumifying, and then it's sticking the the suffix length in it, and then also getting the hashing. So the first thing I do is decide, well, can I do this at all? Every object in GraphBLAS, whether it's user defined or built in, has a predefined hash of that object. And then if I want to compose a bunch of, like, a summaring as a monoid rule multiplier and so forth, I get a new object. Well, if it's a new object that depends on older existing objects, I don't have to rehash the old objects. I just hash the hashes basically together. I combine the hashes together. And you can see that here at the bottom in particular. I have two hashes. I just exclusive OR them together. I get another hash. So I keep this as fast as I can. There's a special case for the hash function. The hash function is uint. It's a 64-bit number. It's uint 64 under one condition only. That is, I can't JIT it. If I can't JIT this this monoid, then I return failure, and basically the JIT says go away. I can't do it, and it returns no value to the caller. It refuses to do it. Why would this happen? Well, this would happen if, say, you constructed a monoid from an operator, and when you built the operator, you didn't tell me, maybe it's a user-defined operator, but you didn't give me the string of the function, the C code. It's like, well, I can't JIT that. Or you didn't give me the name or whatever. You didn't give me enough information to JIT it. So I'd refuse. I can't JIT it. I have to use just this raw function pointer. The JIT's not applicable. So I very quickly have to decide, and I can do this then super quickly. This is if and only I can JIT the thing if and only if this hash is not uint64. Okay, so now I decide I can JIT the thing. Now I have to do all the enumerifications. So this is a process. And this is a very hierarchical process where I now have to enumify a reduce operation. And I have the monoid and have the matrix. Within that, I'm going to have to decide to enumify the matrix and enumify the monoid. How to enumify the monoid? I have to enumify a binary operator. It's nested all the way down. And see, this enumification of a monoid will also be true for the MXM. It has to do other things, but then it also has to call the same enumification of a monoid and an operator and so forth. So you're going to see a lot of reuse in that sense on these different objects. So how do I enumify or reduce? If you go to the JITifier, you enumify. Now I've decided I have a reduce method. Let's enumify it. So it's only 112 lines. I get out the different data types. I get out the opcode of the reduction monoid. No, the operator. Reduce op is the operator. The monoid includes within it the operator as part of its data structure. I get at the two different data types. And I do a quick rename. There's a lot of redundant, it's kind of unfortunate. In the GraphBLAS spec, there's a lot of redundant operators, Boolean operators. Like there's a min Boolean operator. Like that's just and. It's logical and. There's a Boolean times. That's logical and. So if the output is type Boolean, I rename the opcode. Now I have to now I can enumify the monoid. I have the opcode, which could be, and I think I have to pass in. Let's see. No, I don't. This is now just integers based. There's no, the operators are gone. So if these are defined, The opcode's just going to be a special number that says it's some user-defined operator. Okay, I have to numify the monoid first, and I'm going to get some codes that numify the which reduction, which ID value you're talking about, which is the terminal value, as a short code. And at the very end, and then I'll find a bunch of other properties of the monoid and the matrix. So I'll go into these in a minute, but first I want to dive into the final result, what I want to get. Remember, this has to happen on every call. So it's got to be fast. I get this case, it's 28 bits it takes to enumify every possible call to reduce matrix to scalar, every possible one. This is just a macro that helps me shift bits around. So I have 28 bits to pack, and I need to keep track of the 4 bits for the sparsity format of A. 2 bits, no, 2 bits? Well, I need it. Oh, I'm sorry, 1 bit for, yeah, it's 1 bit to note, do you have zombies or not on the input matrix? So there's the input matrix. And what data type is A? There's 14 data types. There's the 13 built-ins, or is it 12? How many? There's 14. There's 13 built-ins, including my complex. And there's the 14th one is all user-defined types. Go there, which doesn't fully specify which user-defined type we're talking about, but that's enough for this encoding. Same thing, the type of the monoid, which could differ because you could typecast. These two don't have to be different. And then which of my built-in reduction operators do we have? There's 23 of them. One of these is, oh, it's user-defined. The ID value, I have 30 different cases. The terminal value, 30 different cases. And has cheeseburger, this is for CUDA only. This cheese is, do you have a, please CUDA tell me if, this is in production. I'm actually using this in production, but I'm not using it later in the CUDA kernels because the CUDA kernels aren't active. Has cheeseburger is a stupid name, but what it means is, does the monoid have a atomic operation that's equivalent to it that different thread blocks can call to write to global memory to atomically update some value? Like if it's plus double, oh yeah, they can do that. If it's user defined, sorry, I can't do that. And other operators don't work either, even if they're built in. So that's what this is determining. It's a single bit. These are the bits. And I packed them into 28 bits. I could use bit, I don't, but I could use like C bit field things. I didn't use those. This is just shift and logical or logical or, sorry, shifts and a logical or together to pack these 28 bits together. And that's the outcome of the Judify reduce, is this code that encodes all, 28 bits that encodes all possible reductions I could see. And I can then, if the hash of the monoid is 0, this is a built-in operator. I don't need to hash the monoid. I hash everything else, but not the built-ins. And then I get the encoding of the K code needs to be stored here as well. And then the suffix length I can get, whether it's built in. Then I look at the monoid name and get the length of it. And then I have the suffix is the name of the operator for the monoid. So that's a suffix, that's a string I have to stick in. So now I've got several things to hash, but I've already hashed the name of the operator into the hash of the monoid. And so I don't need to go and read the string every time and hash the string. The hash encoding then just has to hash a 128-bit number down to a 64-bit hash. It's a very fast hash, the JITifier hash encoding method. It's just a wrapper around a XX hash. It's a very fast hash to get the 64-bit. I make sure I don't get any special numbers and then that's my hash code. So the goal of this encodifying is to create the encoding struct, which is the hash. It's the enumerified code, and the encoding includes the enumerification. It includes the kernel code, which is this is the JIT reduce code, and it includes the suffix length, and then also return the hash value outside of that. So those are the things that are coming out of this method here. But let me dive into these methods now, and please stop me if there's anything that's not clear. I've got to dive into now.
No, I'm
Okay,
following.
well, okay. So I've got to enumerate all possible monoids. So now let's look at, let's go to, you're in the JITify already. We'll go to GB enumify monoid. How do I enumify monoid? Oh, well, I just enumify three things: a binary op, an identity value, and a terminal. There's three things to enumify to be able to enumify the monoid, because I need these three things. How to enumify a bin op? That's a big beast, because there's a ton of operators. Okay. Well, GB enumify a bin op. And you can imagine enumify bin op then will be called by a lot of different methods: matrix multiply, EY's add, accumulator. Everybody goes want to enumerate a binary op. And I treat operators differently if this is being enumerated for a semaring as the multiplicative operator of a semaring. Some of my operators differ, and they have to be handled slightly differently. No, I wouldn't have to, but I realized I could fold together some of my codes, and so I just know how they're being applied. These are my index binary ops. They're already there. As I have GXB first J, GXB second I, and so forth. Those are GRB binary ops that already are positional, already are indexed ops. And that's what I have to have here. But for here, it's false. Right? I don't think I have, you can't use this in a monoid. So the input to this is just two integers. The opcode of the operator and the type code of the data type. Okay, so this is going to produce a number in the range 0 to 255. Now, a monoid can't use all of those because not all built-in operators are available to build into monoids. They're not permitted. And so I go and, user cases are always code 0. I just have to encode all possible sets of operations. Like, for example, the min. Okay, well, I'm gonna want to create potentially 4 different expressions to compute the min of 2 numbers. And this right here, the min Boolean, is a logical AND, which I already got away. I already avoided that in the rename, but I have it here anyway in case it happens. FP32 is going to be different than FP64. One's going to be FBin, one's going to be FBinF. Okay, so the string I want to produce that is the operator shall differ, and so it's function 3 versus function 4. 3 versus 4. And the default, everybody else is going to do an integer minimum. That's a ternary x less than y, result is x else y, and so on. So all these, and some of these are repeats, because this is you're going to see this later on down below, or this one. Max and plus in Boolean are the same, so it produces the same expression. So it's code 17. So I'm giving a code that'll distinguish between all possible strings that I'm going to emit into the macro for the template for that method. So if 2 monoids map to the same string, I can just reuse that same kernel. So this is what this function is doing. It's just a very fast switch case that's deciding which value E we're going to use, and then these numbers. There's a bunch of them. There's 255 max. There's less than that for all operators. you can't use all these for monoids. You can only use the first 32. I think I stop at, if it's less than 32, it's valid as a monoid, and that's it. And like these are built-in operators that mostly can't be used as a monoid, well, except for this one. And so all I have to do is I have to then enumerate all possible strings that I'm going to stick in that macro that defines the operator. And that's it, big switch table. I think it's interesting to dive into, well, what do I do with this number when I want to then compile the kernel? I will have to macrofy, construct all the macros. Well, let's not look at it now, but you're going to see a switch case across this value E from 0 to whatever. It's not 255, it's a little bit less than that, 139. 255 is a no-op that'll emit the string for that number, 0 to 255. I won't go into that just now, I'll do that later. So enumify monoid then is enumify the bin up, and then I have to enumify the identity value and the terminal value of a monoid. And there's, so GB, I have to stick in, I have to know, well, what identity value are we talking about? I have to go, I go from the opcode itself and the type of the operator, I think. This depends on some of them. Yeah, some of these depend on this. To 31 different strings that I'm going to produce for built-in types and operators. 31, I'm going to have to do something different because it's a user-defined monoid. I just have the bytes, so I have to do that differently. But for built-in operators, the value could be 0, it could be true, it could be int 32 max, it could be negative infinity, it could be a bit string, it could be 0 again. And so there's all the different possible ID values. And then all the same thing, all the different values for the terminal value, which looks just like this. It's just finding the terminal instead of the identity value. I'm not actually looking into the object, the monoid object itself. I'm taking the code of the monoid, the opcode of the operator, and picking its terminal value. So enumify terminal looks like this, let's see, where's plus? 31 means you don't have a terminal value. So plus is not terminal. You sum stuff up, you never stop. You have to always keep going. Terminal means a monoid that short circuits, like Boolean and. Once you see a false, you can stop. So the terminal value of and will emit the number false as a string into the code. So it's code 3. Again, just some very fast switch cases. So now I have an encoding of all possible reductions and their operation, their function as a number, as an opcode, if you will, as an enumified code. All possible ID values, of which there are at most 32, and there's a little less than that, but it's the power of 2. And so the ID code, this is 32 cases. It takes 5 bits, the encoding, to represent 5 bits for the terminal value of the total of 28. So that's the monoid. Then I have to do this silly CUDA atomic thing for the 1 bit for the cheeseburger thing. And then I have to enumify the matrix itself. Because all these things play together. I'm going to compile a special JIT just for this format of the matrix, just for this operator, and just for this monoid. And so this has what's the matrix? Well, there's 15 different types of matrices, data types, 0 to 14. I think 0 is user defined, so it has to be named somehow other. Then plus the 13 built-in types, so that's 14 or 15 different types. Oh, 0 is special. I think 0 means I don't care. what the type is. It's type agnostic. Like the first operator doesn't care what the type of the B matrix is. So 0 means I don't care what it is. I'll just take it. I'm not going to read the type. I don't think that's the case that's not the case here in the reduction. I've already gotten rid of that by the caller. So this one won't care about that. But I then have to enumify the sparsity format. There's 4 different formats of the matrix. So that's going to be number from 0 through 0 to 3, which is sparse, hypersparse, bitmap, or full, 1 matrix. And that's going to come down here, 2 bits. Do you have any zombies in your matrix? That's a bit down here. And so that gives me all the possible formats. Now, all the possible reductions, almost. All user-defined operators map to the same code. So to distinguish those, I have to look at their name. And I have to, if they hash together and have the same name, then they're the same. So that's the case where I hash the name, but I have to just make sure the name is the same first of the operator. Okay, so that is, enumify sparsity, that's very simple. Oh, let's see, where am I? Oh, I'm not in the JITfire kernel folder. GB enumify sparsity. 4 numbers. Like, are you sparse? Fine. Are you bitmap? 0. Well, that's just 0, 1, 2, 3, 4. 0, 1, 2, 3 to get me all possible formats. Okay, so I've enumified it. Then let me go to the JITfire kernel. I'm inside and codify reduce. That's the main thing. So I called the JIT. The first thing I do is I call this method. To call this method, I enumify reduce. So now I have a code. I have the code. I stick it in the encoding. The encoding needs more things. It needs the kernel code as well, which is I didn't put in the number. I just kept it outside. And that thing is I haven't shown you that yet. I have all possible JIT kernels have their own code. So which JIT kernel are we talking about here? Well, we're doing code 1. We're doing reduce to scalar. Number 1. I have a placeholder. 0 means there's no JIT kernel, and I don't actually use it, but it's there if I need it. All the dot product. I'm sorry, all the matrix multiply kernels. There's, I don't know, 7 of them. There's nothing magic about these numbers, but I did lump them all to group them together. All the EWISE methods. I have, how many EWISE methods do I have? This is actually an MXM method, but I treat it internally as if it's a EWISE method. It's multiplying a matrix times a diagonal. You don't actually use the monoid. So it fits in the space of a EWISE function. So MXM is actually turning into an EWISE method internally in this case. Other than that, the other ones are originally EWISE, and I don't know, there's a little over a dozen of them, kernels for the EWISE methods. Apply, there's 8 or 10 of those. Build, I've got 1. Select, I've got 3. User-defined types and operators are very specialized kernels. I'll explain those when I get to them. And I have only 5 JITted assign methods. And these were important for the gap benchmarks. And I didn't do the rest because I ran out of steam, but I've got to do them. I've got about 40 more. I don't know how many assign kernels I have. Count them. They're numbered, but they're not implemented yet. These are not implemented. And I've got extract, which is internally I call sub-referencing. I don't have JITified yet. The accum mask phase has a mask kernel, which I don't have JITted, which is when you want to do something fancy with the mask. Chronicle product is not JITted. I have a few other utilities that are not JITted. And then I have CUDA kernels, of which I've got some JITs now working. These are the ones that actually are working in prototype. And this is the JIT code. And it's 32-bit numbers. So I've got plenty of space. And I've decided that anything above 1,000 is a CUDA kernel, just to, if I need to check, are you a CUDA kernel or are you a CPU kernel? And if I needed to pack these in smaller bits, I could if I had to. So that's the unification. I have the kernel unified. I have the K code, which is just a number here, an enum. And then I have the suffix length inside this encoding. That'll tell me if it's built in or not. And that is, let's see, that was up at the top. That was, where was that? Yeah, that was this object right here. That's the encoding. It has that bit shift thingy, all the bits all packed together. And then it has this thing was not bit shift packed, it's just the kernel code, so held separately. And then how many, if you're user defined, you're going to have a string. And that's the length of the string. I store it there. So I hash that. And that also goes in the hash table along with the hash and the actual suffix with with the function handle. Okay. So now that's the entire encodify. I didn't do any string operations. I just did some fast bit shifts, some fast lookup of a hash table. At most, I took a previous, like I had to hash a 128-bit number to a 64-bit number. And I exclusive or that if the monitor has its pre-computed hash, I exclusive or that, and that's the hash of this problem. Unless I can't do it. Say, go away, I can't do you. So the hash of 0 is special. It means it's just a built-in method. It's not actually a hash function. And uint64 max is special. It means I can't hash it. And I know so if the hashing happens to produce those special cases, I just put in a jump number. That's not those special cases. This is exceedingly rare.
Does that cause it to fall through to the generic kernel?
This case, yes.
Okay.
Potentially. Actually, yes, because I try the factory kernel first. Usually call the CUDA kernel first. I try the CUDA if I have it. It don't have it, or other cases that you don't need CUDA, like that ISO case where reducing a matrix to a vector when the matrix has just a billion ones. Like, I don't need CUDA for that. I don't need to call a special JIT kernel for that. I can just use 30 calls to reduce to the operator and get the answer. 2 to the 30, you're done. So I don't need to JIT that. I just call the function pointer 30 times. I don't JIT that at all. I don't have a factory kernel. I have one kernel that does that for all functions with a function pointer. But this case, yes, if I call this method and says, hey, you can't hash this monoid. Oh, see, all built-in ops have a hash that's actually 0. All built-ins, if your hash function is 0 of the object, not of the call to the method, an object, a built-in submarine, a built-in operator, a built-in monoid always has a hash of 0. The hash is not fully computed yet. The hash depends on all this encoding. But if you're built-in, then that's your final hash. You exclusive or with 0, nothing happens. So 0 is special. 0 says if it's in an object, a hash is 0. I don't need to hash any further. I just get the hash of the encoding and we're done. If you're a user defined, and when I create the monoid, it's user defined, I hash it and get its hash function. I look at the string, I look at the data, I get a whole big hash for that, 64-bit hash. But if it doesn't have the string for the operator, it's uint64. It means it's a monoid I can't JIT. And yes, then you would go to generics normally. Unless it's covered by the other special case, like the ISO full case, like, or ISO case, where you're reducing a matrix to a scalar and all the entries are the same. I don't ever JIT any of that. It's never come to this point, and it won't be generic. I guess it is in a sense generic because I'm using function pointers, but it's 30 calls for a billion entries of the matrix. You won't even notice how fast it is. There's no need to JIT that, or even write a kernel for that. Okay, so this is what it means to encodify the reduce method. So if I look at my JIT wrappers, the very first thing it does for GB reduced to scalar JIT, this is the wrapper for GB. I've decided to commit to the JIT. I'll come in here, I call that method you just saw. Please encodify this case. To do that, I get back, I need to get the encoding object, which is this one. And I'll get back the actual string of the suffix if it's not empty. And I have to tell the encodify reduce what kernel it is. There's only one, so it doesn't matter. There's only one reduced to kernel. In other words, this method only accepts that one case. Seems kind of boring. But other encodifiers will encode multiple instances, like up here. Like I will have an encodify for MXM, okay, where the kernel will differ depending on the kernel code, of which there's about, what, 8 of them. Okay, but here there's just one. And then the problem specification, the monoid and the matrix. And I don't have here, by the way, the data type of the result. Where did that go? I don't need it. Well, what if there's typecasting in the result? I'll handle that later. You see, the JIT kernel's job is to only encode to the type of the Z of the operator, the Z type of the operator. The monoid it works in some space, I call it Z. There's Z, X, and Y. X and Y are the two input matrices, like for matrix multiply. The monoid works on Z. If there's a final typecast of the output, well, that's a separate phase. I'll do that later. The JIT kernel is only going to reduce to the type of Z. That's why I call the result Z. And the data type of that void star pointer is the Z type of the monoid, full stop. And I'll do any typecasting outside of this JIT. Okay, so I don't need to know. I don't need to look at that type because I know what it is. It must be the same as the monoid, so that I don't have to push that into the kernel, to the encodify. Okay, so that's the encodification. And now it gets longer. Okay, I have to see, do I have it? Is it in my hash table already? Oh, there you are. And there's the function pointer. Go and call it. And that has to be the grease lightning path. Or, oh, I don't have it. Let's go look for it. I look at the cat. Oh, there it's in disk. I'll load it in. I'll open it and I'll cache it in my hash table, which is why I'm computing this hash function. And I'll insert it into the hash table. And then I'll return the hash function. I'll DLSIM it to find that thing called GBJIT kernel entry point. And then I can then call it. And when I do that, I also put the function pointer in the hash table. And of course, it could fail. Anything can fail. So I think GRB info is my standard error code internally even. And if it fails, I return that it's not successful. GBJITifier load, this is identical for all JIT wrappers. If I do, and the calls are all, they're very similar. Like if I'm in JIT wrapper, all of these JITifier load, all of these are going to call the same thing, JITifier load, and to get a function pointer. Now, and some of the rest of the things will be different to this. So let's look at JITifier. Let's look at JITifier load. Now, this is the thing that's going to do the macrofying and compiling if I need to. So it keeps getting more and more interesting. All right, so I've done, we've seen the, where is it? The encodify reduce. This is built this, and it's called upon an encodify, not an encodify, but a numify of a monoid, which is asked for the numification of a binary operator. It's asked for the enumification of an identity value, enumification of a terminal value, and so forth. So that's all the enumifiers. There's a bunch of enumifiers. And it's gotten back a number. Now the JITifier is going to come in. The JITifier load, this is maybe a misnomer. It's give me the function pointer if it's already loaded, or load it from the disk if it's not loaded but compiled yesterday or last week or something. Or whoops, I didn't find it. Let me go create it and compile it. So it's a doing more than just JITifier load. It's a whole bunch of things. And that's inside this one rather large file. This is a file of length 2,700 lines of code. And the reason I put it all in one file, and usually I'll split a, one file per function, but I need some globals here that all of GraphBLAS needs to use, even if you have different user threads. And so, for example, one hash table, it's in here. It's a global thing. And so I protect it with critical sections. So if you have two user threads talking to the JIT, like only one can compile at a time. It just got too crazy otherwise. There could be some performance issues with this if you have user level parallelism, each user thread wanting to compile JITs at the same time. I could do better to make it more parallel, to let the JIT run in parallel with other JIT kernels. I mean, then they're talking like, oh, do I have it? Oh, I don't have it. Let me go compile it. Well, some other JIT user thread says, oh, let me go call this function. Oh, I don't have it. Let me go compile it. Well, they can't both compile it. So I worry about that, and I just say, sorry, one at a time. And to do that, I need some static global, I need some global space, and I need some global strings. I need the hash table. This is the hash table right here. It's an array of JIT entries that I do my own hashing into it. And I also have other things like a ton of strings. But let me just go from where I was, because you haven't seen the, let's see, the load. Let me just dive in from where. So there's the JITifier load. This is one of the main entry points for to the JIT from the outside, the rest of GraphBLAS. There are others that do other important things. Okay, so what is the goal of this? The goal of this in the end is to produce one thing, a function pointer to the JIT itself, to the JIT kernel itself, and that's the output. Okay, to do that, I need many things. I need to know which family we're in. The JIT family is those groups of kernels. Let's see, where's the JIT family defined? Oh, this is in jitkernel.h. Let me do gb JITifier.h. The JIT family. There's the JIT family right here. Whoops, the top. Here. Those, 44 current JIT kernels I have break into about 9 different families. The reduced family is a family of 1, lonely family, but there are 7 MXMs and so on. The JIT family doesn't actually play much role in this. It is very, I'll show you what impact it has, a very small impact on the actual work that's happening. Mostly like how many bits do I need to put in the file name and so forth in the encoding. But so it's a very small thing that's used. So that doesn't have a huge impact on the outcome. But I do keep it there to speed a few cases up, to handle a few special cases. I need as input the name of the kernel I'm going to compile. Okay. For the, let's see, for the JITifier, we just saw, for the JIT wrapper, GB reduce, there we go. I called it reduce. All right, so what does that turn into? Let me exit from MATLAB here. So that's the name of this particular kernel. It's reduce. So, well, that's just part of the name. If I go to my cache folder, whoops. Here's all my source. Let me go one up level. Okay, here's my cache folder. I'm in my default cache is .SuiteSparse GRB 9.3. The nice thing about this, if I change GraphBLAS at all, like 0.1, 3.9.31, I abandon all previously compiled JITs automatically. So if you upgrade GraphBLAS, I abandon this folder and go to GRB 931. Because I don't know, what if I had a bug fix in one kernel somewhere? I just abandon everything. At the top level here, I have 5 different subfolders. I have source code, which is C. It's also CUDA. I have compiled libraries, and they're broken up into 255 subfolders because I thought one folder would be too big. If I have 10,000 kernels, I don't want to have 10,000 files in a single folder. So this is a folder that's broken up by the last 8 bits of the hash code. So it's a file hash table, if you will. I also have file locking. Whoops. And again, have that split into each subfolder. And I have source. This is all the source code I need to compile my JIT kernels goes here. And that was emitted here by my JIT package, which I have not described. And then I have a temp folder for stuff. And I forget what I put there, like whatever. At the moment, on the top of my head, I can't remember what I put there. Okay, so the JIT family, the kernel name reduce. Oh yeah, I know where I was going. Reduce. So in the C folder, in all the hash buckets, you can look at reduce. And oh, well, I only have CUDA reduce, so that's a different name. But if I were doing, let me reconfigure GraphBLAS. This is my CUDA branch. I'm going to turn off CUDA because I want to stick with the CPU. It's simpler. So let me go back. Let me go to my dev3. Let me recompile GraphBLAS. And I'm going to turn off. I have a hack in my code to force up at the bottom in GRB init. I can hack my GPU code to say, if you have a GPU kernel, use it, and otherwise don't. You know. So now I'm going to never use the GPU. Oh, that's default. No, I want to use this one. Never use the GPU. So I'm going to recompile GraphBLAS here. And I won't abandon my previous kernels because they'll be fine. I normally would just delete them if I am. So let me rerun one of my demos, Gauss demo, and I'm going to pipe it to the output so you can read the output. It's going to take a little while to run, and it's going to compile some kernels, and it just finished. So there's the output. Let me do it again. And oh, that was, well, it's not actually fast because I'm playing games with GraphBLAS and fooling it and forcing it to do more work to compile kernels again, even though I ran it twice. All right, so let's look at the first case. I turn on the burble. When I turn on the burble, this is the first case. You can see here I'm actually using CMake to compile all my kernels. I'm messing with the JIT. I'm turning it off and on. And if I look for the word JIT, you'll see, oh, I need to compile it. Okay, compile it. Oh, it's already there. I'll load it and so forth. This is the first time. Oh, I must have, oh, this is a CUDA JIT. I am gonna blitz my kernel, previous kernel. I'm gonna obliterate I have just a shell script that deletes that cache folder. Let me rerun the Gauss demo. So this is now just a CPU compilation. And the burble is going to, and it's going to take a while because it's got all the kernels to compile. I think it's not going to be any CUDA JITs, just CPU JITs. It has to compile a lot of JITs. Because when I'm running on the CUDA dev mode, I turn on the compact option. So there are no factory kernels available. So everything has to be compiled with a JIT. So the first time is really slow.
You started this a while back, right? It's still going?
Oh, yeah, it's actually still going. There we go. I mean, look at all the JITs it had to compile. Oh, it's compiling CUDA JITs. I thought I turned those off. Shoot. Oh, I didn't want the CUDA JITs. All right, well, let's leave the CUDA JITs. They're not that different. Doesn't much matter. I thought I would turn off the CUDA JITs. Shoot. Oh, yeah. Okay. So now just got CPU JITs. All right. I guess that's strange. Why am I getting CUDA JITs? These are like JIT compiling CUDA. I didn't think it was going to happen. Okay, well, my hack is not obviously working. It's just a hack and it's just in development anyway. So, I mean, I could just recompile GraphBLAS. It takes a while to do all of it though, so I won't bother to do that. So anyway, you see now a bunch of kernels. Here's all my kernels. There's some few CUDA kernels in there. I'm not sure why those are still there, but and some of these are this one's interesting. It doesn't have a suffix. This is using built-in types, but I had to JIT it because it's either in compact mode or maybe did typecasting. Compact mode means there are no factor kernels available. But the point of what I wanted to show you was that the name of that kernel is called reduce, and that goes into this part of the name of the file and also the name of the function. I preface it with just the same thing, gbjit __, double underscores delimits. Here, the first chunk is the name of the method. The second thing is the code, which is not a hash function. It's what goes into the hash function. It's those bits. It's the enumerified bits. And then the suffix was, oh, this is the add Gauss method. So what does this thing look like? And I have two of them.
Well, is there two of them? I mean, other than the
Yeah,
two
there's
and
two
the
of them.
three.
Right. You see, they differ. So let's do a diff between them. Yeah, they're different. Whoops. They do differ. And here's how they differ. I think one's bitmap, one's full. So here we go.
Oh, I see.
They
Yeah.
have different names, but the matrix formats are different.
Yeah.
And
Okay.
it's now a compile time constant. One of them says
Because in the program you constructed the two different types, or the problem used the two different formats.
Exactly.
Okay.
The demo was walking through, and it's opaque. The user application doesn't know what formatted I'm just picking, but I picked, oh, that's a full matrix. Oh, that's a bitmap matrix. Different kernels. And they're almost identical. Otherwise, like I have macros that tell me, how do I get access to the entry from the matrix? Oh, if it's bitmap, I have to check the bitmap. If it's not bitmap, the bitmap says, well, it's true. It's always there. Come on, what are you talking about? This is a full matrix. Don't need to look up the bitmap. The bitmap is true. How do you ask how many entries are in the matrix? Well, if it's bitmap, you have to be careful. You have to look it up. And if it, otherwise, I can just take the product. I probably could get rid of this dependency here. And how many do you? I could have made this AN vowels, but I take the product. That's yeah. I shouldn't do that. That should just be AN vowels always. Anyway, I have to think about why I'm doing that. I've, and then what's the name of the kernel? So I had to name it slightly differently. And now you don't see code there. Like, okay, where's the code? You won't see any code in that kernel yet because it's in a template and it just has the file. The template file is the same, but it'll templatize internally to say, oh, your bitmap, do something different versus your full or sparse and so forth. But they are two different kernels, entirely different kernels that get compiled and called. And it depends upon, that will be given to this in the encoding of the problem. One will say it's bitmap, one will say it's full. This encoding will have a code in it that is 83F2 as a hexadecimal number because it's bit, so I can read it better. This will be F3. And if I walked it through far enough, you would see that, let's just look at these two files. One of them, they're both doing reduction using the add Gauss monoid with the Gauss type. So this is the Gauss type, and this is a user-defined monoid. This is the Gauss, add Gauss operator. And the Gaussian integer is an integer with real and imaginary parts, because why not? It's a thing, a Gaussian integer. It's a math, it's a defined, it's a complex number that based upon integers, not reals. And so the add Gauss just does what you think, add the reals and add the imaginaries together. It's like a complex add, but they just happen to be integers. These are the macros that define what you want to do. How do you how do you call the update add method? How do you call the update method? How do you declare an identity value? Well, I can just do a mem set here. It's user defined. I have the user defined type there. It's all zeros. The matrix is bitmap. And then here's the actual code for the kernel. It's a template. And this is something else, which I'll get to in a minute. So this function here eventually is going to write this file and compile it. But I first have to have the input that describes the instance I'm looking for, the encoding, the string with a suffix, which in this case would be add Gauss, as the const char add Gauss. The suffix, the K name would be reduce here. The JIT family would also be reduce. And then I also need these things. Now, this function, JITify load, is used for all across GraphBLAS. So everybody needs at most one semmering. Oh, but I don't need it for the monoid reduction. So this is null. I'm not going to use it. The monoid I'll use, but it might also use an operator, like for, I guess, a cum may need an operator. So I'll pass it there if the JIT kernel takes it. And then I may have to have up to 3 different types. And the 3 different types here are, so if you think about, say, a call to GRBMXM, how many types are we talking about? We could be talking about potentially 7 different types. I only need actually 3 here. The reason is, I'll explain at this point, is a good point to explain. So GRBMXM, you have 4 matrices, CMAB, that's 4 types there. And then you have the semmering, which I call ZXY types. The multiplicative operator has inputs types of X and Y, output type is Z, and the monoid works across Z, so that doesn't add a new type. So there's 7 types total. All right, well, those types, let me see if the X and the Y and the Z type Well, I already, if it's a semmering, I already have it. It's right there in the semmering. I don't need to pass it in specially. It's baked into the semmering. So type 1 and type 2 and type 3 would be the types of the input matrices and perhaps the type of the output matrix C. The type of the mask is different. I don't actually need to know, well, I forget. I might need to know the mask, the type of the mask somewhere.
Yeah, isn't there
I think
masking by value?
yeah, there's a masking by value. So that's going to be one of the types as well. Probably for MXM, I think actually I have those. Yeah, that's what I do. Let's look at DRB MXM. Yeah, there's mask by value. So that would be one of the types, I think. So if I go to the JIT wrappers, it turns out I need at most 3 different types. And depending on how the JIT family will use those 3 types in different ways. And the reduced to scalar will just use one of those types. So let's look at, say, the Saxby 3 JIT. And this will take in a mask. And then I probably come down here and, oh, no, I don't actually, let's see. Oh, I remember what I do. Okay. The masking type is special. It's actually part of the encoding, and I no longer need it at this point because if you mask by value, it must be a built-in type. You cannot mask on user-defined types. So I don't need the whole rich property of the M masking matrix type. I just need to encode the type and I'm done. I have enough information just in the bits. So it's encoded it's put into the encoding. So I no longer need it here. I only need it here in the case that it's user-defined. I need more information about the type. But if it's built in, I don't actually need any of this information here. Built-in types are already in the encoding anyway from here. Okay, so that's why 3 types are enough. If any of these matrices are user-defined, C, A, or B, then I need to know their full description of their types. I think that's why. Yeah, that's why. So the masking is special. I have it in Codify for Enumify for the mask as well to get the mask bits, but there's only a certain number of types you can use, and you can't use user-defined types as valued masking. You can use them as structural, but then it's structural. That's a bit that says, hey, it's structural. I don't care what the type is then, whether it's built in or not. It doesn't matter. That's why I don't need the mask type as one of these 3 types. So this for the GRB MXM, that would be the 3 types for C, A, and B. And any other types are either already folded into the encoding for the mask or into the semmering and or the monoid, one or the other. Here for JITifier load, so here we're looking at encodifying one of the matrix multiplies with the JIT. Okay, you can see here I need the semmering, but I don't need the monoid. It's already inside the semmering, so that's all I need to pass into it is the semmering. So it doesn't get the monoid or an operator at all. So these 2 for MXM would be empty, would be null. I don't need it. Okay, so we called JITifier load, and yeah, we're getting close to 3 o'clock. This is going to be a long thing.
Well, if it's a good stopping point, we can pick it up next
Yeah,
week.
let me give you the sort of leap ahead here. The leap ahead is I write this file.
Right.
Okay. If I need to, I write this entire file, and this entire file then has, if I need it, the type def of the type we're talking about. It has 2 things, both the type def and a string stuck in there, which I'll use down below. And then I need the function and the string also of that same function. These are identical. One's hidden in a string, one isn't. Okay, then I need to know, well, then, how do I apply the operator? What's the Z type itself? The Z type there, it's Gauss. Templating in C is pound define a macro, pound include the template. And that's what I'm doing here. So there's all the source code. That is then the GBJIT kernel. But I have another method inside of here called the JIT query, which is is important error checking thing. Or it's like, what if someday you compile a user-defined data type, you call it Gauss type or something, or you create a function called add Gauss. Okay, and you change the name of you keep the name the same, but you change the string. Oh my goodness. Now, this kernel here I'm looking at, this is just called reduce add Gauss. Like, what if you change the type of Gauss? What if you change the string for add Gauss? Well, do I have to hash? I do. I hash the string? But I mean, the name of that file would be absurdly long to make it unique. I don't do that. So what I do is that if I find that if it changes, I have a way of detecting it. Now it's expensive to check this, so I only do it when I load the kernel into memory. When I do the DL open, okay, I get the library loaded, and I have two entry points into this library. GBJIT kernel to call and do the work, and GBJIT query to ask you, well, who are you anyway? And that's what this function is. I can ask it, what's your hash code? If that doesn't match, something bad has happened, so throw it away and recompile. Oh, you were compiled for version GraphBLAS 9.3. Well, I'm 3.931, and I don't take you. Go away. What is your strings? And there's up to 5 different strings for these definitions of types and operators. 3 types, 2 operators is enough. If I do fusion, it'll be more, because you get more types and more operators all in one kernel. But right now, and so I can ask the library, okay, give me your entire function definition as a string, and I'll do a string compare to make sure you're the right one. That's expensive. I don't do that in every call to this kernel. I do it only when I load it into memory. So if I just freshly compile it, I'll check it then to make sure it'll always work. But if it's an old one, it's compiled it last week and you recompiled your code, and I load it and I thought, well, this is different. And I throw it away, I DL close it, and I recompile. And I check the value of the identity, and actually do the check inside the query function. And I return back true or false. Whether the identity and if I need to check the terminal value and the identity value, I can make sure the size hasn't changed. I can then declare the identity value and check it. If I need to compare that terminal value, this has no terminal value. So I check all those things. That's the JIT query. So the goal then of this JITify load is if it doesn't see this particular JIT kernel with its types, it's like, oh, I need to build this function. And so what it first has to do is write the file we just saw. And in fact, I actually have, as an example, in this JIT, I have to, let's see, whoops. We're getting to a stopping point here soon. Okay, so these are all my JIT kernels. I have a folder called JIT kernels, and they only have 2 subfolders, include and templates. Include and template are subfolders that will always go into what I call the JIT package. That's source code that goes in that cache folder. I haven't explained that yet. But the JIT kernel for reduce has some extra magic in it. Let me look at it. It has a ton of comments in it. This if def for comments only has an example of what it is to specialize this method. This is the reduce kernel AC1FBB2, whatever that is. Well, it's plus double, and it defines the monoid as plus double type the matrix is bitmap, and there's the entire method. And it's built in, so I don't need to, I just need to know it. I don't need to know the definition. The encoding has the full description. So there's no need to check the strings if it's built in. So the query is really simple. Like, do you have the right hash code? Great, we're done. Are you for the right version of GraphBLAS? Great, we're done. That's all we need to verify. Because I don't want to accidentally get a JIT kernel that's been compiled from a previous version of GraphBLAS. That could be disastrous. And then here's the kernel. I have the prototype of the method, which is the same as you saw before in the where was it? JIT wrapper, GB reduce, whoops. The scalar JIT. So let me kind of take you big picture all the way to and fro. So this function here potentially writes out this templatized instance, like the macro header in the cache folder, compiles it, and that compiled code pulls this code in as the template that's now reading in the template code to actually do the work, which is the whole algorithm. But what's interesting about this algorithm is that I have two variants of it, but it's known at compile time, which I have. Do you have zombies or not? Are you bitmap, or is your panel size equal to 1? If so, there's one case that can handle zombies. It's a simpler algorithm, and this is an algorithm that does reduction across panels. It doesn't do one at a time. It does a whole bunch at a time, so it vectorizes more nicely. That's the algorithm, but it's all compile time selected as to which algorithm I'm picking. And so this is this prototype. It's the same prototype up here because I reuse it in so many different places. I didn't want to. I hid it inside a macro, and that prototype are these parameters basically. Result, where any workspace I need, the input matrix, and that's it. So that's the job. And actually, I have as comments here the prototype itself, just for grins to see. You can see it. This is the same prototype has been used up here as the function pointer to this particular method. The name of this function is always gbjitkernel, because that's what I'm going to do. DLSim, I load a library, I'm going to look it up. Well, let me look for gbjitkernel. I'm not looking for this funky name of gbjit reduce AC1FBB2. That's the full name of the method. But inside the library, it's called always, every JIT kernel is always called gbjitkernel. But except for one case. And that is, and again, this is the broad brush overview, and before we get to the details of how this happens, and that's the pre-JIT case. Once you compile a bunch of JIT kernels, and say you want to run on the Apple iPad, you can't put a compiler on the iPad, and the system pass a string to system doesn't work. Okay, because it doesn't allow it. Well, you can still have on any system, you can have what I call pre-JIT kernels. You run GraphBLAS, you run some applications, it generates all these JIT kernels, and you look at your cache file, your .SuiteSparse GRB, you copy all those C files that I generate back into GraphBLAS in this special folder called pre-JIT. You rebuild GraphBLAS. The CMake structure says, the CMake build system says, oh, look, there's some C code in pre-JIT. Let me put it in. And let me compile them right now. And when it compiles them, it doesn't set the gbjit runtime, because now they all have to have the unique names. And now gbjit runtime is false, it's not defined. And so now, well, okay, I can't call it gbjit kernel. I have to call it by its special name to distinguish it from all the other JIT kernels that are pre-JIT kernels in the library. They're all baked into libgraphblas.so now. So that's a pre-JIT. So this is handling the pre-JIT case. If you're not a runtime JIT, you're a pre-JIT kernel, and now these two methods have to have their own unique names that are hard. They're loaded with libgraphblas.so. And of course, I got to know which method to call, so I have a table of these functions that I build as well. and their names. The name is AC1FBB2. When do I call that? Well, I've got to demacrify. That's the demacrify. I've got to get the name and get out of the name the code and the name of the suffix and everything. So I can say, oh, you're this one. As if I had JITted you at runtime, this is your hashing. This is your JIT structure that goes in the hash table. And so that's that. The pre-JIT kernels go through the same process here. I still have to find them in the hash table. So I still have to encode them. But when I go and load them, I realize, oh, look, you're already in the hash table and you're this function right there. I already have you. You're built in now. So the JIT and the pre-JIT look very similar all the way through the code. It's just the pre-JIT are already compiled and built into libGraphBLAS, and the JIT ones are not. The JIT runtimes are not. But to do that, I do have to specialize right here. So each of them has a unique name now. So that's the big picture of going all the way through the encoding and then look it up in the hash table. Oh, oops, it's not there. Quick, write this file. And that is done. And then go and compile it, load it in, that kernel in my hash table, return the hash function, the kernel function, and then call it. And then the JITifier then has all these macrofy methods, which take the encoding and they take the data type and they take the semiring and they take whatever they need and they're spitting out the strings, which are the pound define macros. They're writing to this header file and I stick in, which kernel are you? Oh, you're reduce. Okay, so I'm going to pound include template, GBJIT kernel name. So that name is picking amongst all of these. So if I pound include that name right there, comes from right there, tells me which source code I need to pound include. And if I want this to be the CUDA reduce, I would look for a CUDA JIT kernel. It's in a different folder, but it'd be called JIT kernel, CUDA reduce. It'd be a totally different kernel, of course, different code, but it'd look very similar otherwise. The CUDA case is actually interesting to look at. Again, this is still a high level view, so I'm gonna stop soon here, but we do need to go dig in deeper as to, well, how does this macrofication process work? You've seen all the encoding, and I've only just barely scratched the surface of the JITifier.c files. This file right here, it's a 2,000 line code. I haven't actually gone into it, how it works yet. But it needs to macrofy stuff and everything. But another interesting thing here in the CUDA folder, I also have a CUDA reduced to scalar JIT, which by golly, that looks awfully similar to this thing. Yeah, it is. In fact, if you do a diff, it's the only difference is what's the kernel number, what's the name of the function. If you look at these lines of code and these lines of code, they're the same except the name of the method. That's it. This is CUDA reduce on the left and reduce, quote unquote, on the right. Otherwise, they're absolutely identical. And the other thing is the code is different. One is CUDA reduce, and it's over 1,000 in the enum space. And this is like kernel number 1. This is kernel number 1001. So I know it's for CUDA. I think I turned off the CUDA reduce, but the only difference, if I looked, I don't have time to we're running out of time here, so I don't want to go too much. So I don't have any CUDA kernels here anymore, I think. Certainly not any reduced ones. But if I look at the CUDA versions of these two, like the addgauss.cu, it would have the same encoding. The name would be CUDA reduce, and the only difference, it'd be like one line difference. Whoops. Oh, I'm already editing it. Up the top would be pound defined CUDA kernel. That'd be one thing that's different. And the other thing that would be different would be, this would be JIT kernel CUDA reduce.cu. That's it. So it's a different source code, CUDA related. Everything else would be the same. This would look all the same. In fact, I even include in here, whoops, CUDA, there are two little CUDA related things already in here because I'll need it for the CUDA kernels. Like, do you have cheeseburger? CUDA atomic user is true. Do you has an atomic update? That's the cheeseburger thing, I think. No, that's for CPU as well. What's your, let's see. Well, there's two things I need to do on CUDA that are different than I do on the for atomic updates than I need for the CPU. So I just put it in there. Anyway, and the CPU side ignores those two definitions. But if I were to generate the same kernel for the CUDA kernel, they would look absolutely identical, except for the very top would be a pound defined GB CUDA kernel to tell me this is a CUDA kernel. And this name would be different. Oh, and these names would be different. This would be a JIT CUDA reduce 83 FEEE2 AdGauss. It'd be otherwise the same name. And this would be template JIT kernel CUDA reduce.cu. And there's your CUDA kernel. So it's folded in perfectly. Joined the two kinds of JIT kernels are joined at the hip. They share all this infrastructure.
And just sort of differ in their template.
Yeah, they differ in their templates, right? They have different, like here's the template, here's the CUDA templates. Oh, they're up here. If I go to my, here, let me go to my source folder. So this was emitted by GRB init. So this is all the source code I need to compile all of my JIT kernels. Goes in what I call the JIT package, which I won't describe yet how to do that. I'll do that later. It's 27,000 lines of code. It includes include files, which are not source files. They're just headers. And it includes source code, which is in the template folder. And there's lots of stuff in here, including, where was it? You saw here, JIT kernel reduce, but you see also all the CUDA kernels are here too. And there's CUDA reduce. They're very different algorithms, but they're all sitting in here in one big template folder. And there's some other CUDA stuff for the .3 product. Other kernels I need inside CUDA, which I rename CUDA. I name CUDA. These are now not generated by the. So these are all the source code for all of my kernels, and they're actually used identically for my factory kernels as well. I use the same algorithms. The factory kernels are baked in, and the JITs are not. But this source code is the same. The JIT package is, and I'll show you the process. But when I do a CMake build, it builds a file called a GRB JIT package. I put in there compressed source code. So I have a CMake build process, which I compile and run a program, which reads all the source code. I say that, hey, I need all these to go in my JIT package. It reads all those files one at a time. It reads in the ASCII file. It calls the compression, Z standard compression method, which is already inside GraphBLAS. And I emit a bunch of bytes as a C code. And then when GRB init is called, I go look at your cache folder and I say, do you need source? Oh, your source code is already there. You're good. Or not. Oh, I need to put source code here. Hang on. And I iterate through this source file, and it's about 300 kbytes compressed. And
it's just literal C arrays of compressed code.
Oh yeah, it's literally just bytes. It's literally just. I could show you. It's really kind of cool. It's very simple. It's in the. I have a folder called the GraphBLAS JIT package, and I have this file here is an automatically generated file, and like my reduce method. This is CUDA stuff. Where's, yeah, that the JIT kernel template, the JIT kernel reduce, okay, is this set of bytes from here to here. It's 131 lines of just numbers. This is my source code. And then I have a big table of them all and their name. So when I go in and want to emit this, where's my reduce? That one file, okay. I have everything I need. I have the size once it's uncompressed, the size that's compressed. I have the bytes, which is 2,564 bytes long, and the name of the file I want to produce. And then I have a little GRB init calls a JITifier to say, oh, I need to create the source code, please. And it reads this whole thing and spits out the source code right here. And also
Cool.
GraphBLAS.h is there.
Yeah.
So the advantage here, I had to do this JIT package trick because otherwise the library, the compiled library, needs its own source code. Like, where is
Right.
it?
Yeah.
If you're a Linux distro manager, you don't want to bundle, so you can bundle source code, but I didn't want to like, require they do that. Well, I don't need
Yeah.
all my source code
Yeah.
anyway.
Just pack
I
it
want
into
a
the
single,
library.
yeah, I want a single, and the other advantage is that then what if I get the wrong source code? Like, what if I've got a libgraphblas.so, it's compiled with, and you get the different version of the source you find and use a mismatch? Well, then that's a nightmare. That's segfault city. Okay, so I don't want that to happen. I have a similar problem with, and I'll explain to this next time. And this is the idea of the JIT callbacks. Okay, so some of these JIT kernels depend on GraphBLAS. Like I call the JIT kernel and it wants to call, they want to call me back to do some utility method that doesn't need to be JITified. So I have one method for everybody. Well, so they link, I have to link when I bring in the library, it needs to link against dash L GraphBLAS maybe. Well, which GraphBLAS? Well, the one that's calling it. Well, but if you just do like CMake with dash L GraphBLAS and like, there's my library I'm linking in, I get a different GraphBLAS library, different version. Right? That would be a nightmare as well. So I don't do that. I don't link this library. If I go here to say that the lib folder, okay, if I do, let's see, LDD of one of these guys, there's no dependency on GraphBLAS, but it does call GraphBLAS, the library. How? Well, it's very simple. I just made myself a little struct of function pointers and I put in there like I need about 12 or 13 or 14 different functions that my JIT kernels need to call back into. Everybody that needs any callback methods, I just pass this one struct down. And then any method that needs, oh, I need those three methods, they just extract the function pointers. They're function pointers. And they call me back through function pointers. In other words, I pass down the function pointers that they can call me into. And then I know I'm going to get the right functions, the right
Right.
versions. They'll
Yeah.
call back into me. Say, here, call me. Here's my name. Here's my number. If you need to call me, here's my number. And then I don't have to link against some graph L dash graph clause.
That might be wrong or in the wrong
That might
path
be
or
the wrong
yeah.
version. Right.
Yeah.
That would be a nightmare. So it has to be and that makes the compiling and linking of these JIT kernels easier. I don't have to find a library. They depend
Well, and there's just
on
there's less failure points.
exactly.
Yeah.
Exactly. This was really hard to get working, to figure out all these failure points because I would fail. I failed and ooh, because at first I thought, oh, just link against myself. How hard? Oh, that's really hard.
Yeah.
That's
Right.
yeah, it's a failure point. It was just a nightmare getting it to work
Right.
and to
Yeah.
reliably link against the right thing, and it wasn't. So I created this callback mechanism.
And it's like an
And
environment variable could break you in that case, right?
oh yeah, yeah.
Yeah.
It's just other would be a nightmare. And then the other issues is where do I find my own source? Oh, that's easy. It's just right where? Oh, failure point. Oh well. Oh, how is this going to work in a Linux distro anyway? How do I find my own source? Well, I bundle it into the binary. It's crazy, but it works. And in this binary is already the CUDA stuff in production. I'm not calling it, not using it, but it's already there. So in the released version, this is the released version you're looking at. Well, this isn't, but the released version has these CUDA kernels in it already. They're just not being used. So, okay, well, yeah, it's 3:20. We should stop here. But yeah, the JIT is a big beast. You've seen this whole arc of, oh, I want to call the CUDA, I call the JIT wrapper, and it calls the encodifier that says, here's the instance you're looking for. The JITifier comes in, the JITifier load, and which I haven't dug into the details yet. That says, oh, it's in the hash table already, or no, I got to go compile it, or I can load it, or whatever. Puts in the hash table, returns the function pointer. If I need to compile it, I go through the macrofy process to create those headers. Then once it's compiled and loaded, I just have the function pointer pulled out of the hash table, and there's your function pointer, and call it. And that has to happen really fast if it's already in memory. I still have every time I have to look up that hash table, but it's pretty fast. Now there could be a trade-off here. I haven't worked this out because every method I could punt and say, like, you're reducing a matrix of 4 entries to a scalar. I may already have it compiled. It could work for 1 billion entries or 2 entries. It's the same kernel. It may take longer to look it up in the hash than just to call my generic method. Like, this is 5 nanoseconds, this is 3 nanoseconds, whatever it is. Okay, I don't yet, but I could do the following. I could say, well, at some point, it's not even worth calling the JIT, just call the generic method. Function pointers, it's going to be faster than looking up the table. I don't have that threshold yet. You know, I will have it for the CUDA side of life, because I will have to keep track of when do I want to call CUDA or not. Because maybe it's so small, problem so small, I'll just do it on the CPU anyway. I have unified shared memory on CUDA, and I might decide to keep, but I will try to keep track of where I last touched this part, each parts of these matrices, this data structure, and I'll look at this and decide, oh, last time I touched it was on the GPU, so let me do it on the GPU. Last time I touched it on the CPU, but oh, this is a big problem, big by some threshold, and therefore let's just do it on the GPU. It'll be faster. Or you might tell me, please do this on the GPU with a GRB get set kind of idea. You could say, please do this matrix on the GPU. Okay, I'll do it there. So you could guide me. Otherwise, I'll do it heuristically. I'll make some decision between do I want it on GPU or CPU, and hopefully will make the right decisions based upon where the data already is, I think, where I think it is going to be. I don't have this mechanism all in place yet. Let's see, because that's going to be based on benchmarking and heuristics and such. So next time, let's dive into the core of the JITifier.
Cool. Yeah, and also we were talking about segueing from JIT to MXM as kind of the foundation for MXM. So that'll be like a good transition, I think, for next time is dig into the core.
Yeah. Yeah, I didn't show you the reduce algorithm itself. I just showed there's the template. Imagine.
Right.
I probably should show you that just to see one of them, because it's the simplest template you can imagine. It's not too trivial, but it's a lot simpler than MXM. But I need to show you this whole macrofy. How do I, and because these are things I'm going to have to change a little bit for the new index binary op as well. I already almost support it because I've got some built-in operators that are very They depend on the index, so it's not going to be total break the code kind of event to put in index binary ops. But that's going to be a big change. I'm going to have to do that in a very unstable development branch for a while. It'll be broken until I get it working. But that's going to be my next big project for GraphBLAS, is to do those. The other thing I need to do is I've only got 44 JIT kernels, and I need about 80 of them more. Right? I've got way more I need to write, and I could write still more, because if you look through the top level source code, there's a ton of pragma OMP star.ch. Okay. Whoops. Okay, these are all things. Oh, OMP parallel. Okay, these are all my parallel loops that are never JITted yet, because most of them don't need to be, because they only depend on the pattern, say, or they're just iterating. I don't need to JIT them because they don't depend on the data types, say. And there's a bunch of them. There's I don't know, 100 more of them. There's no need to JIT them because there's only one version of them needed. Well, but what if I go to different integer sizes for the matrices? Well, then I have lots of variants, and I would need to JIT those. So those would then need to be JITted for to handle the different integer sizes. And then what about CUDA, right? You want to do this work on CUDA? Well, that has to also be JITted. So there's two reasons to JIT all these things. If I'm just walking across the pattern of the matrix doing stuff, well, wait, we're supposed to do this on GPU, right? Well, I'm currently don't have the hooks for that. So I've got at least however many that. If I just count those, that's 186 parallel loops in all of GraphBLAS. I have to have 186 kernels for those, potentially, maybe less, probably less. And then I also have other things I've designated as kernels to write, but I don't have them yet. Because if you look at these kernels, these are what I've JITted here. These are all my JIT kernels. These are JIT kernels that correspond to every place where I have a suite of factory kernels. Okay, not just methods that are only generic. But right now, when I started the JIT, I only did those. Those methods that have factory kernels, I'll do JIT kernels for, because that's where performance is critical. These methods are generic only. If there's a data type, if there's an accum operator, function pointers, mem copies. So these methods, these assign methods are not as fast as they could be. Some of these as well, like the Chronicle product is generic only. So that gives me, that's 87 out of, that's about, I've got 44 JIT kernels. I need about 43 more just to cover these cases. Then of course there's all the CUDA kernels, which I've now got 8 or so on that order of magnitude. And then that doesn't count the 186 parallel for loops, which are walking across doing something. What are they doing? They're walking across integers, probably. I have to look at each one. Now, some of those won't be individual CUDA kernels. Some of those will be like a bunch of parallel loops together. So glue it together into one operation. So let's clump them together. There'll be fewer than 186, because you won't want to just CUDify every parallel for loop. That's kind of strange. You probably want to group those into like, let's not do these sets of loops. Let me do something totally different in CUDA for those sets of loops. But it's going to be that's going to be a process to get those all done. But some of those I may not ever have to do, because maybe Some of those loops are parallel, but they're fine on the CPU. Yeah, we could do them in CUDA, but we'll just leave them there. Do it on the CPU, whatever. Because they're not used too often, say. And that's the beauty of unified shared memory. Any piece of hardware, any accelerator that says, I don't care, here's a pointer. Where is it? I don't care. I'll handle it for you. The hardware just does it. If you have a non-uniform memory space, just give me a uniform pointer. And if you need to make it move, fine. It's just that pointer. This is the data I want, and just do it. And it just works. Whatever device grabs it, if it needs to move the memory around, move it. It's like a page fault, right? I don't want to have to write a virtual memory system. You used to do that. Do you remember the days of overlays? Did you ever write code with an overlay? Before virtual memory.
Not really.
I did. I did.
Yeah. I remember like himem.sys.
Yeah, that's kind of like an overlay.
Something like that.
On the Windows, right? Yeah, it was bad there too. Yeah, that's like an overlay.
DOS,
Just like DOS. It's like I have this memory space and I have all this data, and like, okay, overlay this data with this data, and then you got to bring in your other data, and you had to actually manage your own virtual memory. It was a nightmare. We don't have to do that anymore. So.
All right. Well, I think this worked out pretty good. This is a good long one. I'll as usual, I'll send you guys the link when Zoom's done processing it.
Sounds good.
And I'll keep you guys up to date on